The age of the universe is constrained to approximately 13.8 billion years, a value derived from multiple independent and highly consistent observational frameworks. These include precise measurements of anisotropies in the cosmic microwave background radiation, determinations of the Hubble expansion rate via the cosmic distance ladder, stellar evolution modelling of the oldest globular clusters, and predictions from Big Bang nucleosynthesis regarding primordial light element abundances. The convergence of these methods within tight statistical uncertainties makes this estimate one of the most robust in modern cosmology. Except that when astronomers look at the oldest objects in the observable universe, objects that should, by definition, be younger than the cosmos that produced them, they keep finding things that do not fit. Stars whose age estimates exceed the age of the universe, particles that were released before the first atoms formed, structures whose origin traces to conditions that preceded the universe's own formation, signals that carry information from epochs our instruments cannot directly observe and our theories cannot fully describe. These are not fringe anomalies dismissed by the mainstream. They are confirmed, peer-reviewed, published findings that sit at the centre of ongoing debates in cosmology and astrophysics, pointing toward the same uncomfortable conclusion, that the boundary between the universe and whatever came before it is not as clean as the standard picture assumes. Methuselah's star. The star designated HD 140283 sits approximately 190 light-years from Earth in the constellation Libra, close enough, by cosmic standards, to be studied in extraordinary detail with modern instruments. It is a subgiant star, a classification indicating that it has exhausted the hydrogen fuel in its core and begun the slow expansion toward the red giant phase that marks the final chapter of a Sun-like star's life. Its surface temperature is approximately 5,777 Kelvin, essentially identical to the Sun's, but its luminosity is slightly higher and its radius slightly larger, consistent with its evolved status. None of these properties are remarkable. What is remarkable is its chemical composition, and what that composition implies about when it formed. HD 140283 contains almost no heavy elements. In stellar astronomy, all elements heavier than hydrogen and helium are collectively called metals, regardless of whether they are chemically metallic, and the abundance of these elements relative to hydrogen is called the metallicity. The Sun has a metallicity of approximately 1. It contains roughly the same proportion of heavy elements as the interstellar medium from which it formed, which has been progressively enriched by billions of years of stellar evolution. Older stars, which formed earlier in the galaxy's history, when fewer stellar generations had lived and died to produce and distribute heavy elements, have lower metallicities. HD 140283 has a metallicity approximately 250 times lower than the Sun, a value so extreme that it places the star among the most metal-poor objects in the entire Milky Way, a population called Population 2 stars that formed in the galaxy's earliest epochs when the interstellar medium was still nearly pristine. This chemical signature is the first line of evidence for HD 140283's extreme antiquity. The star formed from gas that was barely enriched above primordial composition, gas that had seen only the very first generation of stellar evolution before being incorporated into this star. The small amount of iron and other heavy elements present in the star represents the contribution of a tiny number of earlier stars, possibly among the very first generation of stars to have formed in the universe. This alone suggests HD 140283 is among the oldest stars in existence. The stellar evolution models, which use the star's luminosity, temperature, and composition to estimate how long it has been burning hydrogen, produced an age estimate that made the scientific community sit up and pay close attention. The 2000 analysis by Howard Bond and colleagues at Penn State University, using Hubble Space Telescope observations to precisely determine the star's distance through parallax, and thereby its absolute luminosity, produced an initial age estimate of 16 billion years, older than the universe by a margin of 2.2 billion years. This result was not a rounding error or a preliminary finding. It was derived from careful, rigorous stellar modelling using the best available stellar evolution codes and the most precise available measurements of the star's properties. The finding generated immediate attention precisely because it was taken seriously. It was not the product of a fringe analysis, but of mainstream stellar astrophysics applied to an extraordinarily well-characterized nearby star. The subsequent decade saw sustained effort to resolve the discrepancy. The most important single revision came from a 2013 study by Bond and colleagues that incorporated revised distance measurements from improved Hubble Space Telescope astrometry, achieving a parallax precision of approximately 0.14 milliarc seconds, one of the most precise parallax measurements ever obtained for a star. The improved distance measurement revised the star's absolute luminosity downward slightly, which in turn reduced the inferred age. The 2013 analysis produced a best fit age of 14.46 billion years, with an uncertainty of plus or minus 0.8 billion years. At the central value, the star is still 660 million years older than the universe. At the lower end of the uncertainty range, the youngest plausible age given the measurement uncertainties, the star is 13.66 billion years old, marginally consistent with a universe of 13.8 billion years, but only at the edge of the allowed range. The uncertainty in the stellar age estimate comes from several sources, each of which has been carefully characterized. The primary source is the uncertainty in the helium abundance of the star, the fraction of the star's mass that is helium rather than hydrogen. The helium content affects the rate at which hydrogen fusion proceeds in the stellar core, and therefore the rate at which the star evolves, directly influencing the relationship between the star's current luminosity and its age. The helium content cannot be directly measured in a star like HD 140283, because helium produces no spectral lines in the visible wavelength range for stars of this temperature. It must be inferred from theoretical models, and the uncertainty in the model-inferred helium abundance propagates into an uncertainty in the age estimate of several 100 million years. The second source of uncertainty is the treatment of microscopic diffusion, the process by which helium atoms slowly sink through the stellar interior under gravity, while hydrogen floats upward, gradually changing the composition of the outer layers and affecting the stellar model's predictions. The magnitude of this effect in the very oldest metal-poor stars is uncertain, and different treatments of diffusion give different age estimates by margins comparable to the measurement uncertainties. The third source is the nuclear reaction rates used in the stellar models, particularly the rate of the oxygen-16 plus helium-4 reaction that governs the late stages of helium burning and influences the stellar structure in ways that affect the main sequence turn-off point from which the age is derived. What is striking about this situation is not that the central age estimate is discrepant with the age of the universe. Given the accumulated uncertainties, the discrepancy is not statistically overwhelming. What is striking is that after more than 2 decades of sustained effort to resolve the problem, using increasingly precise observations and increasingly sophisticated stellar models, the discrepancy has not been eliminated. It has been reduced, and the current situation is one of marginal consistency rather than clear inconsistency. But marginal consistency is not the same as agreement. The star's central age estimate still places its birth before the Big Bang, and the discrepancy will only be definitively resolved when either the stellar age uncertainties are reduced substantially below their current level, or the age of the universe is revised upward by a corresponding amount. That second possibility is not as outlandish as it might seem. The Hubble tension, the discrepancy between measurements of the current expansion rate of the universe from the cosmic microwave background and from the local distance ladder, implies that if the local distance ladder value is correct, the universe may be somewhat younger than the CMB derived estimate, which would worsen the Methuselah problem. Conversely, if the CMB derived expansion rate is the more reliable one, the universe's age is approximately 13.8 billion years, and the Methuselah star's age estimate needs to come down by at least another several hundred million years to achieve comfortable consistency. Both outcomes are scientifically possible. Neither has been established, and HD 140283 continues to burn quietly in Libra, 190 light-years away, carrying an age that sits uncomfortably close to the beginning of time. The cosmic neutrino background. Every second, approximately 330 billion neutrinos from the oldest source in the observable universe pass through each cubic centimetre of space, including the space occupied by your body, the space inside every atom of every molecule of air you are breathing, the space between the atoms of the screen you are reading this on. These particles are not from the Sun, whose neutrino output accounts for a separate and far smaller contribution. They are from the cosmic neutrino background, a bath of relic particles released into free propagation when the universe was exactly 1 second old, at a temperature exceeding 10 billion Kelvin, in conditions so extreme that nothing resembling matter, chemistry or structure as we understand it had yet formed. They have been travelling ever since, cooling as the universe expanded, carrying within their quantum states information about a moment in cosmic history that no other observable phenomenon can access. To understand why the cosmic neutrino background is so extraordinary, it is necessary to understand what the universe was like at 1 second of age. At this moment, the universe was a superhot plasma of fundamental particles. Quarks had already combined into protons and neutrons during the first fraction of a second, and the plasma now consisted primarily of protons, neutrons, electrons, positrons, photons, and neutrinos, all in thermal equilibrium, interacting continuously with each other through the fundamental forces. The temperature was approximately 10 billion Kelvin, which is roughly 700 times hotter than the center of the Sun today. And the density of the plasma was so high that even neutrinos, particles so weakly interacting that a light year of solid lead would stop only about half of them at present-day energies, were trapped in thermal equilibrium with everything else. The universe was opaque to neutrinos as completely as it was to light. As the universe expanded and cooled, a critical temperature was reached at which the weak nuclear force interaction rate, the rate at which neutrinos were being created and absorbed through reactions involving protons, neutrons, and electrons, fell below the expansion rate of the universe. At this point, the average neutrino could no longer find a partner to interact with before the expansion carried potential partners out of range. The neutrinos decoupled from the rest of the plasma and began streaming freely through space. This moment of decoupling, called neutrino freeze-out, occurred when the universe was approximately 1 second old, 380,000 years before the photons of the cosmic microwave background were released. The cosmic neutrino background is therefore 380,000 years older than the cosmic microwave background, making it the oldest detectable radiation in the universe. After decoupling, the relic neutrinos preserved a snapshot of the plasma conditions at the moment of their release, specifically the temperature and the distribution of neutrino energies, which followed a thermal distribution characteristic of a particle species in equilibrium. As the universe expanded, this temperature was redshifted downward, cooling the neutrino background in direct proportion to the scale factor of the universe. Today, the cosmic neutrino background has a temperature of approximately 1.945 Kelvin, just barely above absolute zero, and slightly cooler than the cosmic microwave background temperature of 2.725 Kelvin. The small difference in temperature arises because after neutrino decoupling, the annihilation of electrons and positrons heated the photon plasma, but not the neutrinos, giving the photons a slightly higher temperature than the neutrinos from that point onward. The cosmic neutrino background's temperature of 1.945 Kelvin makes its constituent neutrinos extraordinarily difficult to detect. Neutrino detectors work by relying on the neutrino's weak nuclear force interactions with ordinary matter, and the interaction cross-section, the effective target area that a neutrino presents for interaction, decreases with decreasing neutrino energy. At the energies corresponding to a temperature of 1.945 Kelvin, the Relic neutrinos are so cold and their energies so low that their interaction cross-section with ordinary matter is many orders of magnitude smaller than for the higher energy neutrinos from the Sun or from nuclear reactors that existing detectors can measure. A neutrino detector of the kind currently in operation, a tank of liquid argon or a sphere of ultra-pure water, would need to be scaled up by an incomprehensibly large factor to detect the cosmic neutrino background directly. Despite this detection challenge, the cosmic neutrino background is not merely hypothetical. Its effects on the early universe are imprinted in the observables that cosmologists can measure today. The number of neutrino species, 3 in the standard model of particle physics, affects the expansion rate of the early universe through its contribution to the total energy density of the relativistic plasma. This effect propagates into the predictions for the primordial abundances of helium and deuterium produced during Big Bang nucleosynthesis, and into the pattern of acoustic peaks in the cosmic microwave background power spectrum. The Planck satellite's measurement of the effective number of relativistic species at the time of CMB emission, a parameter called N effective, is consistent with the standard model prediction of 3.046 species, which includes the 3 known neutrino flavors plus a small correction from partial decoupling effects. This agreement between the measurement and the prediction, to within measurement uncertainties of roughly 5%, constitutes indirect confirmation that the cosmic neutrino background exists with the properties the standard model predicts. What the cosmic neutrino background carries beyond its confirmation of the standard cosmological model is information from the first second of time that no other observable can access. The cosmic microwave background gives us a snapshot of the universe at 380,000 years. The neutrino background, in principle, would give us a snapshot of the universe at 1 second. The neutrino energy spectrum, if it could be measured, would encode the temperature of the plasma at neutrino decoupling, the baryon to photon ratio at that epoch, and potentially signatures of any non-standard physics that operated in the first second of cosmic history. Any new particle species that was relativistic at the time of neutrino decoupling would have contributed to the energy density of the plasma and left an imprint in the neutrino background's temperature and spectrum. The cosmic neutrino background is a time capsule from the first second of existence, and humanity does not yet have the tools to open it. The Ptolemy experiment, currently in development, represents the most ambitious attempt to change this situation. Ptolemy aims to detect the cosmic neutrino background by measuring the tiny enhancement in the rate of beta decay of tritium, a radioactive isotope of hydrogen that would be caused by the capture of relic neutrinos on tritium nuclei. The enhancement is extraordinarily small. The capture rate is expected to be approximately 4 events per year per 100 grams of tritium, requiring a detector with sub-electron volt energy resolution and extremely tight control of all background processes. Whether Ptolemy can achieve the required performance is an open engineering and physics question. But the scientific prize, the first direct measurement of particles from the first second of the universe's existence, has made the attempt one of the most consequential experimental programs in physics. Primordial black holes. The black holes that astronomers study in the present-day universe fall into 2 established categories: Stellar mass black holes, ranging from roughly 3 to perhaps 100 solar masses, form when massive stars exhaust their nuclear fuel and the core collapses under gravity in a supernova explosion. Supermassive black holes, ranging from millions to tens of billions of solar masses, sit at the centers of most large galaxies and grew through a combination of gas accretion and mergers over billions of years. Both categories have in common a single essential prerequisite. They require pre-existing matter, stars, gas clouds, stellar clusters, as their raw material and progenitors. They are products of astrophysical evolution. They require a universe that has already produced structures to consume. Primordial black holes are different in kind, not just in degree. They are not products of stellar evolution or galaxy formation. They did not require pre-existing structure. They formed directly from the density fluctuations of the primordial plasma during the first fraction of a second after the Big Bang, in some theoretical models within the first millisecond, and in the most extreme versions within the first microsecond. At these early moments, the universe was so hot and so dense that regions where the local density fluctuation exceeded a critical threshold, roughly 30% above the average density, would undergo gravitational collapse faster than the pressure of the plasma could resist. The result was a black hole formed directly from the plasma itself, before any star had ignited, before any galaxy had assembled, before any atom had formed. The theoretical framework for primordial black hole formation was developed primarily by Stephen Hawking and Bernard Carr in the early 1970s. Hawking and Carr showed that the mass of a primordial black hole formed at time t after the Big Bang is approximately equal to the mass contained within the cosmological horizon at that time, the radius within which information could travel at the speed of light in the time t. This relationship between formation time and mass spans an extraordinary range. A primordial black hole formed at 10 to the minus 5 seconds after the Big Bang would have a mass of approximately 10 to the 15 grams, the mass of a small mountain compressed into a volume smaller than a proton. A primordial black hole formed at 1 second would have a mass of approximately 10 to the 5 solar masses, comparable to the smallest known supermassive black holes. The mass distribution of primordial black holes therefore spans roughly 20 orders of magnitude, depending on when, during the first second they formed. This mass range has direct implications for their observability and their longevity. Hawking's 1974 discovery that black holes evaporate through the quantum mechanical emission of radiation, now called Hawking radiation, showed that the evaporation rate is inversely proportional to the square of the black hole mass. Very low-mass primordial black holes would have evaporated entirely within the current age of the universe. Black holes with initial masses below approximately 10 to the 12 kilograms, about the mass of a mountain, would have fully evaporated by now. Black holes with masses above this threshold would still exist, potentially in large numbers, drifting through space as invisible gravitational objects detectable only through their gravitational effects on surrounding matter and light. The question of whether primordial black holes account for some or all of the dark matter is one of the most actively debated topics in cosmology. Dark matter constitutes approximately 27% of the total energy density of the universe, but has never been detected through any interaction other than gravity. If a significant fraction of dark matter consists of primordial black holes in a specific mass range, most observational constraints currently point to a window between roughly 10 to the minus 16 and 10 to the minus 11 solar masses. They would be invisible to most electromagnetic observations, gravitationally lensing background stars with a characteristic signature that microlensing surveys can detect. Several gravitational microlensing surveys, including MACHO, EROS, OGI, and more recently, the Subaru Hyper Suprime Cam survey, have placed constraints on the primordial black hole fraction of dark matter across different mass ranges, ruling out primordial black holes as the dominant dark matter component in most of the probed mass ranges. However, significant windows in the mass distribution remain observationally unconstrained, and primordial black holes could still constitute a fraction of dark matter without contradicting existing observation. What makes primordial black holes particularly extraordinary in the context of cosmic prehistory is not their role in dark matter, but their nature as relics from an epoch that predates all other known astrophysical objects. A primordial black hole formed at 1 microsecond after the Big Bang is not merely old, it is a gravitational fossil from conditions that are genuinely alien by any human standard. Conditions in which the universe was a featureless, scalding plasma of fundamental particles in which no structure of any kind existed. The black hole itself is a singularity in space-time, a point where the ordinary description of physics breaks down, surrounded by an event horizon that has been propagating outward through the subsequent 13.8 billion years of cosmic evolution. It has survived the epoch of nucleosynthesis, the epoch of recombination, the cosmic dark ages, the formation of the first stars and galaxies, the assembly of the Milky Way, the formation of the solar system, and the entire history of life on Earth, accumulating no physical changes other than the extremely slow evaporation from Hawking radiation. If primordial black holes exist in the mass range that survives to the present day, they are not merely among the oldest objects in the universe. They are the oldest gravitational structures that physics can describe, predating every other category of astrophysical object by billions of years. The detection of gravitational waves from merging black holes by the LIGO and Virgo observatories has added a new potential diagnostic. Several of the detected binary black hole mergers have involved masses, particularly in the range between 3 and 10 solar masses, that are difficult to explain through known stellar evolution pathways. Some researchers have proposed that these could be merging primordial black holes, whose mass distribution would be expected to include objects in exactly this range if they form from density fluctuations during the epoch of quantum chromodynamic phase transition, when quarks combined into protons and neutrons at approximately 10 microseconds after the Big Bang. The statistical evidence for a primordial black hole contribution to the LIGO-Virgo event catalogue is currently inconclusive, but has generated substantial theoretical interest. If confirmed, it would represent the first direct detection of objects that formed in the first microseconds of the universe's existence. The inflaton field. Every object in this list exists within the universe, within the space-time that began with the Big Bang and has been expanding and evolving for the subsequent 13.8 billion years. Even the cosmic neutrino background, the oldest directly detectable radiation, was produced within the universe's first second. Even primordial black holes, the oldest gravitational structures, formed within the first fraction of a second. There is one entity in cosmological physics, however, that does not fit this description, an entity whose existence is inferred as the precondition for the universe itself, rather than as a product of it. This entity is the inflaton field, and its relationship to the beginning of the universe is unlike anything else in physics. Cosmic inflation is the theoretical framework, first proposed by Alan Guth in 1980, that describes an epoch of exponential expansion in the universe's earliest moments. Expansion so rapid that the observable universe grew from a region smaller than a proton to a scale roughly 10 to the 26 times larger in approximately 10 to the minus 32 seconds. The motivation for this framework comes from 3 observational facts about the universe that the standard Big Bang model cannot explain without it. The first is the horizon problem. Regions of the universe that are too far apart to have ever been in causal contact, to have exchanged light or any other signal, nevertheless have nearly identical temperatures, suggesting they were in thermal equilibrium at some earlier time. The second is the flatness problem. The spatial curvature of the universe is measured to be extremely close to zero, a condition that requires the energy density to be fine-tuned to within 1 part in 10 to the 60 at the Planck epoch to be consistent with the observed flatness today. The third is the absence of magnetic monopoles and other exotic relics that grand unified theories predict should have been produced in enormous quantities in the early universe. Inflation resolves all three problems simultaneously. The rapid expansion drove a small, thermally equilibrated region to encompass the entire observable universe, diluted the spatial curvature to near zero regardless of its initial value, and diluted the density of exotic relics below the threshold of observability. These resolutions are elegant and compelling, but they require the existence of a specific physical entity that drove the inflation, a scalar quantum field called the inflaton field that existed in a high energy state called the false vacuum, and whose energy was responsible for the exponential expansion. When the inflaton field transitioned from the false vacuum to a lower energy state, a process called slow roll followed by reheating, the stored energy was converted into the particles and radiation of the hot Big Bang plasma, initiating the epoch of conventional expansion and structure formation. The inflaton field's properties must satisfy several observational constraints. The spectrum of density fluctuations it produced, the statistical pattern of initial density variations that seeded all subsequent structure, must be nearly scale invariant, meaning fluctuations of similar amplitude on all accessible scales. This prediction of inflation is confirmed by measurements of the cosmic microwave background power spectrum, which shows a nearly scale invariant spectrum of primordial fluctuations consistent with the simplest inflation models. The inflaton field must also produce a small but potentially detectable background of primordial gravitational waves, tensor perturbations of space-time that are a generic prediction of inflation. The amplitude of this gravitational wave background, parameterized by the tensor-to-scalar ratio R, is the primary remaining test of inflation, and current upper limits from CMB polarization measurements constrain R to be below approximately 0.036, a result that already rules out the simplest version of Guth's original inflation model and constrains the shape of the inflaton field's potential energy function significantly. What makes the inflaton field philosophically and physically extraordinary is the question of where it came from. The inflaton field drove inflation. Inflation produced the universe as we know it. The inflaton field therefore predates the universe in a meaningful physical sense. It was the energy reservoir from which the Big Bang's heat and matter emerged, and it existed in whatever physical state preceded the inflationary epoch. The inflaton field is not a product of the universe. The universe is a product of the inflaton field's evolution. This raises an immediate question that physics cannot yet answer. What set the inflaton field into the false vacuum state from which it subsequently evolved and drove inflation? The inflaton field required initial conditions, a specific value and a specific rate of change, to undergo the slow roll evolution that produces an observationally consistent inflationary epoch. Those initial conditions were not themselves produced by inflation. They preceded inflation. They belong to whatever physical state existed before inflation began, a state that our current theories describe only approximately and that may involve physics beyond the standard model, quantum gravitational effects in which space-time itself is not a well-defined classical entity, or some mechanism of eternal inflation in which the field began in the false vacuum through a quantum fluctuation from an already inflating background. In the framework of eternal inflation, developed by Andrei Linde and Alexander Vilenkin in the 1980s, the inflaton field is not unique to our universe. It is a feature of a vast, possibly infinite inflating background. A multiverse in which quantum fluctuations continuously nucleate new inflationary bubbles, each developing into a universe with its own physical constants, particle content, and laws. Our universe is one such bubble. The inflaton field that drove our inflation is not an isolated entity, but a local manifestation of a field that permeates the entire multiverse, driving inflation everywhere and always, with individual universes forming as local accidents of quantum mechanics. In this picture, the inflaton field did not have a beginning. It exists timelessly in the inflating background, as permanent and as fundamental as space and time themselves. Or perhaps more fundamental, since it generates the space and time of each bubble universe from its own energy. Whether eternal inflation is physically real is not currently testable. By construction, the other inflationary bubbles are beyond our observational horizon. But the framework is the most natural extension of inflation theory, and it implies that the inflaton field is not merely older than our universe. It is older than the concept of time as it applies within our universe. It belongs to a different category of existence than anything within the 13.8 billion year history that physics can observe and describe. Every particle in every atom of every star in the observable universe is a byproduct of this field's evolution. The Big Bang was not the beginning of everything. It was a local event, the conversion of one region of the inflaton field's energy into the matter and radiation of a new universe, in a process that has been occurring throughout an eternal inflating background that our physics can point to but cannot see. Prestellar molecular clouds. Between the emission of the cosmic microwave background at 380,000 years after the Big Bang and the ignition of the first stars at somewhere between 100 and 400 million years after the Big Bang, the universe existed in a state for which there is no present-day analogue. There were no stars. There was no light from any luminous source. There was no ionizing radiation capable of energizing atoms into emission. The universe was filled with hydrogen and helium gas, slowly cooling, gradually accumulating in the gravitational potential wells of dark matter halos, flowing along the dark matter filaments of the cosmic web's emerging skeleton. This epoch is called the Cosmic Dark Ages, and the objects that populated it, the primordial molecular clouds from which all subsequent cosmic structure ultimately descended, are among the oldest physical structures in the observable universe. The primordial molecular clouds of the Dark Ages were not the same as the molecular clouds of the present-day galaxy. In the Milky Way today, molecular clouds are chemically rich environments containing hundreds of different molecular species: water, carbon monoxide, methanol, ammonia, complex organics, formed from the heavy elements produced by billions of years of stellar nucleosynthesis, and recycled through the interstellar medium by stellar winds and supernova explosions. The molecular clouds of the cosmic dark ages contained essentially none of these molecules. The only elements available were the hydrogen and helium produced in the first 3 minutes after the Big Bang by primordial nucleosynthesis, along with trace amounts of lithium, deuterium, and helium-3. The molecular species that could form from this primordial composition were correspondingly limited: molecular hydrogen, hydrogen deuteride, and helium hydride, the simplest possible molecules. Helium hydride, designated HEH+, holds the distinction of being the first molecule that formed in the universe. It appeared when the universe was approximately 100,000 years old, before recombination, when the temperature had dropped enough for helium ions to capture electrons and form neutral helium atoms, which could then bind to protons to form HEH+. This molecule was the universe's first chemical bond, the earliest moment when the electromagnetic force between electrons and nuclei organized matter into anything more complex than isolated particles. The detection of HEH+ in the interstellar medium of a planetary nebula in 2019 by the Sophia Observatory confirmed that this molecule, predicted by astrochemical models of the early universe for decades, could survive and be observed in the present-day universe. Its presence in the primordial dark ages was even more fundamental. It participated in the cooling of primordial gas, facilitating the collapse of the first dark matter halos into structures dense enough to eventually form stars. Molecular hydrogen, H2, was the dominant coolant in the primordial molecular clouds of the dark ages. The cooling of gas from the thousands of Kelvin characteristic of the post-recombination universe to the tens of Kelvin needed for gravitational collapse and star formation requires the gas to radiate energy away. In present-day molecular clouds, this cooling is dominated by rotational and vibrational transitions of carbon monoxide and other heavy element molecules. In the primordial dark ages, these molecules did not exist, and the only available coolant was H2, which is a less efficient cooler than CO because the hydrogen molecule is symmetric and lacks a permanent electric dipole moment, making its radiative transition slower. This inefficiency of primordial cooling directly shaped the properties of the first stars. The less efficient cooling meant that primordial gas clouds had to become more massive before they could fragment into individual star-forming cores, leading to the prediction that the first stars were far more massive than typical present-day stars. The first generation of stars, called population 3 stars, formed from these primordial molecular clouds and had properties radically different from any star visible today. Current theoretical models predict typical population 3 star masses between tens and hundreds of solar masses, with some models allowing masses up to 1,000 solar masses or more under specific initial conditions. Stars this massive have main sequence lifetimes of only a few million years before exploding as supernovae, seeding the surrounding gas with the first heavy elements and ionizing the surrounding intergalactic medium with their intense ultraviolet radiation. The transition from the pristine, heavy element-free molecular clouds of the cosmic dark ages to the chemically enriched star-forming environments of the first galaxies was driven entirely by these first stellar explosions, and the properties of that transition, how quickly the first metals spread through the intergalactic medium, how efficiently population 3 supernovae mix their ejecta into the surrounding gas, are directly encoded in the chemical abundances of the most metal-poor stars in the present-day universe, including HD 140283. The primordial molecular clouds of the cosmic dark ages have left their mark not just in the chemical composition of ancient stars, but in the large-scale structure of the universe. The pattern of density fluctuations in the primordial gas, which grew from the quantum fluctuations of the inflaton field, amplified by inflation, and imprinted on the plasma as the acoustic oscillations seen in the cosmic microwave background, determined where the primordial molecular clouds would collect and where the first stars and galaxies would form. The cosmic web that defines the large-scale distribution of matter in the present-day universe is the gravitationally evolved descendant of the density pattern in these primordial clouds. Every galaxy cluster, every cosmic filament traces its structural origin to the distribution of primordial molecular gas in the universe's first few 100 million years. Detection of the cosmic dark ages directly, observations of the primordial molecular clouds before the first stars ignited, is one of the most ambitious goals of next-generation astronomy. The 21-centimetre emission line of neutral hydrogen, produced by a spin-flip transition of the hydrogen atom, provides a potential tracer of the neutral gas distribution during the dark ages and the subsequent epoch of reionization. Radio telescopes capable of detecting this signal at the relevant redshifts, roughly redshifts of 10 to 50, corresponding to cosmic ages between roughly 70 million and 500 million years, would be able to map the three-dimensional distribution of neutral hydrogen during the dark ages and trace the formation and evolution of the first luminous structures. The hydrogen epoch of reionization array and the square kilometre array's low-frequency component are designed to pursue this measurement. And the lunar surface electromagnetics experiment on the far side of the Moon, shielded from Earth's radio frequency interference, represents an even more ambitious approach to accessing this epoch. If successful, these observations would provide the first direct images of the universe before the first stars, the primordial molecular clouds in their pristine pre-stellar state, the raw material from which everything else was eventually assembled. Baryon acoustic oscillations. One of the most remarkable facts about the observable universe is that the positions of galaxies across billions of light years are not random. At first glance, the large-scale distribution of galaxies appears chaotic, a complex web of filaments and voids, clusters and sheets, with no obvious regular pattern. But statistical analysis of galaxy surveys reveals a subtle but unmistakable signal. Galaxies are slightly more likely to be separated by a distance of approximately 490 million light-years than by slightly smaller or larger separations. This preferred separation distance, the Baryon acoustic oscillation scale, is imprinted on the spatial distribution of matter throughout the observable universe, from the nearest galaxy clusters to the most distant quasars. It is a fossil of sound waves that propagated through the primordial plasma in the universe's first 380,000 years, frozen into the structure of matter at the moment of recombination and preserved, essentially unchanged, for the subsequent 13.8 billion years of cosmic evolution. Understanding what baryon acoustic oscillations are requires understanding the physical conditions of the primordial plasma before recombination. In the first 380,000 years of the universe's history, ordinary matter, protons, electrons, and the photons that interacted with them constantly through electromagnetic scattering, formed a single, tightly coupled fluid. Gravity pulled on the matter component, trying to compress over dense regions into denser concentrations. The radiation pressure of the photons resisted this compression, pushing outward against the gravitational collapse. The competition between gravity and radiation pressure set up oscillations. Acoustic waves propagating through the plasma at approximately half the speed of light, driven by the same physics as sound waves in air, but in a medium of incomprehensibly higher energy density and temperature. These sound waves propagated outward from each initial overdensity in the primordial plasma, carrying a shell of compressed matter away from the center. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, the moment of recombination, the photons suddenly decoupled from the matter and streamed freely outward. The coupling that had been driving the acoustic waves was gone. The sound waves stopped propagating, and the matter distribution at that moment, with the shell of compressed baryons sitting at a specific distance from each initial overdensity, was frozen into place. The distance that sound could travel through the plasma between the Big Bang and recombination, called the sound horizon, determines the preferred separation distance that shows up in the galaxy distribution today. The sound horizon at recombination has been calculated to approximately 150 megaparsecs in co-moving coordinates, approximately 490 million light-years in today's expanded universe. This number is not merely a theoretical prediction. It is calculated from first principles using the known physics of the primordial plasma, the electromagnetic interactions between photons and electrons, the nuclear physics that determined the proton-to-neutron ratio and the helium abundance, and the gravitational dynamics of the dark matter halos in which the baryonic overdensities were embedded. The same physics that correctly predicts the pattern of acoustic peaks in the cosmic microwave background power spectrum also predicts the baryon acoustic oscillation scale in the galaxy distribution, and the observed agreement between the predicted and measured scale at different cosmic epochs has made baryon acoustic oscillations one of the most powerful standard rulers in cosmology. The Baryon acoustic oscillation signal was first confirmed in the large-scale distribution of galaxies in 2005 by Daniel Eisenstein and colleagues using data from the Sloan Digital Sky Survey, which measured the three-dimensional positions of approximately 46,000 luminous red galaxies. The statistical analysis found a clear excess in the galaxy correlation function at a separation of approximately 150 megaparsecs, exactly where the Baryon acoustic oscillation signal was predicted, at a statistical significance of approximately 3.4 sigma. The result has since been confirmed and refined by dozens of subsequent surveys, including the Wiggle-Z survey, the BOSS survey, the eBOSS survey, and most recently, the first data release from the Dark Energy Spectroscopic Instrument in 2024, which measured the Baryon acoustic oscillation scale using over 6 million galaxy spectra across a broad range of cosmic epochs, with a precision exceeding 1%. The philosophical implications of Baryon acoustic oscillations go beyond their role as a cosmological tool. They represent the direct imprint of physical processes from the universe's first 380,000 years on the largest observable structures in the present-day cosmos. The positions of galaxies, of the trillions of stars contained within them, of the billions of years of stellar evolution that produce those stars, of whatever planetary systems orbit those stars, were influenced by the pattern of sound waves that propagated through a plasma 10,000 times hotter than the center of the Sun, in conditions that bore no resemblance to anything in the present-day universe. The architecture of the cosmos was partially determined before atoms existed. More than that, the Baryon acoustic oscillation scale is a direct measurement of the sound horizon at recombination, and the sound horizon depends on the ratio of the baryon density to the photon density in the primordial plasma, a ratio that was fixed during the first 3 minutes of the universe's existence, during Big Bang nucleosynthesis. The Baryon acoustic oscillation signal in the galaxy distribution is therefore a fossil not just of the acoustic oscillations of the pre-recombination plasma, but of the conditions established in the first 3 minutes of cosmic history. When the DESI survey measures galaxy positions billions of light-years away and finds the Baryon acoustic oscillation peak at a specific separation, it is measuring a quantity determined by physics that operated when the universe was 3 minutes old. The sound waves of the primordial plasma have left a permanent imprint on the arrangement of the universe's matter, and that imprint, detectable today by counting the positions of millions of galaxies, carries information about conditions that existed before any structure, before any star, any galaxy, any atom of hydrogen had formed. The CMB cold spot. In the full sky map of the cosmic microwave background, the temperature pattern of the oldest light in the universe, there is a region in the southern sky, in the direction of the constellation Eridanus, that is significantly colder than its surroundings. Not slightly colder. The cold spot is cooler than the average by approximately 70 microkelvins, which may sound negligible, but represents an extreme outlier in the statistical distribution of temperature fluctuations across the CMB sky. The cold spot spans approximately 10 degrees on the sky, corresponding to a physical scale at the distance of the last scattering surface of roughly 1 billion light-years. It was identified in 2004 by Vielva and colleagues using data from the WMAP satellite, and its existence has been confirmed repeatedly, including in the Planck satellite's higher resolution and better characterized maps. No standard cosmological model can fully account for it. To understand why the cold spot is anomalous requires understanding the statistical framework within which CMB temperature fluctuations are interpreted. In the standard model of inflation, the primordial density fluctuation that seeded the CMB temperature pattern are drawn from a Gaussian random field, a specific statistical distribution in which the amplitude of fluctuations at any given angular scale follows a bell curve, and in which fluctuations at different scales and locations are statistically independent. This Gaussian prediction is one of the most fundamental outputs of simple inflation models, and the CMB temperature map is statistically consistent with Gaussianity at most scales and locations. The cold spot is an exception. Its combination of depth, how cold it is relative to the surroundings, and angular size, how large it is on the sky, makes it a feature that should occur by random chance in a Gaussian CMB map with a probability of approximately 1 to 2%, depending on the specific statistical test applied. 1% probability is not impossibly small. Unlikely events do occur, and the CMB sky contains enough distinct regions that a 1% anomaly somewhere might be expected on probabilistic grounds. But the cold spot has attracted sustained attention beyond its raw statistical improbability because of the difficulty of finding a convincing conventional explanation for it within the standard model. The most natural explanation for a large cold region in the CMB is the Sachs-Wolf effect associated with a large underdensity, a cosmic void along the line of sight. Photons passing through a large void lose energy as they climb out of the void's gravitational potential, producing a cold imprint in the CMB at the void's location. This is the integrated Sachs-Wolf effect, and it is a standard CMB foreground from the large-scale structure of the universe. The problem is that the void required to explain the cold spot through the integrated Sachs-Wolf effect is extraordinarily large. Calculations suggest that a supervoid at a redshift of approximately 0.2 to 0.3, with a diameter of roughly 1 billion light-years and a density deficit of approximately 30% below the cosmic average, would produce a cold spot of approximately the observed angular size and temperature decrement. A supervoid of this scale is not observationally forbidden, but it is rare in the predictions of the standard lambda CDM model, significantly rarer, in fact, than the cold spot itself, which is part of why the supervoid explanation has not achieved universal acceptance. Multiple studies have searched for the supervoid in galaxy surveys that should reveal underdensities along the line of sight to the cold spot. Some studies found evidence for a void-like structure in the region. Others found a less pronounced or absent underdensity. The observational situation as of 2025 is that a moderate underdensity exists in the direction of the cold spot, but it is insufficient by itself to fully explain the temperature decrement through the integrated Sachs-Wolf effect. The alternative explanation that has generated the most theoretical discussion is the bubble collision hypothesis. In the framework of eternal inflation, our universe formed when a region of the inflaton field transitioned from the false vacuum, the high-energy inflationary state, to the true vacuum, nucleating a bubble of post-inflationary space-time. If other bubbles nucleated nearby in the inflating background, which eternal inflation predicts should occur continuously throughout the multiverse, there is a possibility that two inflationary bubbles could collide. A bubble collision would leave a distinctive imprint on the CMB of the interior universe, a circular region of enhanced or diminished temperature with a sharp boundary defined by the intersection of the two bubble walls. The cold spot has the circular morphology and the approximate scale expected from a bubble collision signature, which is what prompted Feeney, Johnson, Mortlock and Peiris to analyse the Planck CMB map specifically for bubble collision signatures in 2011. Their analysis found 4 candidate bubble collision features in the Planck data, with the cold spot being the most prominent. They calculated the Bayesian evidence for the bubble collision model relative to the standard model without bubble collisions, and found weak but non-negligible preference for the bubble collision interpretation for the cold spot. The analysis was methodologically careful, and the result was not a claim of detection, but a quantified statement that the data are slightly more consistent with a bubble collision than without one, at a level insufficient for a scientific claim, but sufficient to motivate further investigation. Subsequent analyses using improved CMB data and different statistical frameworks have produced varying conclusions, with some finding marginal support for the bubble collision interpretation, and others finding results consistent with the standard model with a statistical fluctuation. The bubble collision hypothesis, if correct, would be among the most profound observational findings in the history of science. A bubble collision imprint on the CMB would be direct evidence that our universe is embedded in a larger inflating multiverse and that at least one other inflationary bubble exists beyond our cosmological horizon. The cold spot would not merely be an anomaly in the oldest light in the universe. It would be a scar left by the collision of our universe with another universe, a mark imposed on the structure of our space-time from outside, a fossil of an interaction that occurred before our Big Bang had finished establishing the physical laws and initial conditions that govern everything within the observable cosmos. The investigation continues, and the cold spot remains, stubbornly cold, in the southern sky. Ancient quasar black holes. In July 2017, a paper published in Nature announced the detection of a quasar designated J1342+0928 at a redshift of 7.54, making it, at the time, the most distant quasar ever discovered, seen when the universe was only 690 million years old. At its centre, powering the extraordinary luminosity of more than 40 trillion solar luminosities, was a supermassive black hole with a mass of approximately 780 million solar masses. The light from this object had travelled for over 13.1 billion years to reach Earth, carrying information about the physical conditions of the early universe within the first 6% of its current age. The discovery was immediately recognised as a profound challenge to the standard model of black hole formation and growth, because the physics of black hole accretion imposes strict limits on how quickly a black hole can grow, limits that appear to be violated by the existence of this object. The relevant physical constraint is the Eddington limit, named after Arthur Eddington, who first derived it in the context of stellar physics. The Eddington limit defines the maximum luminosity and, correspondingly, the maximum accretion rate, at which a spherically accreting object in hydrostatic equilibrium can operate without the radiation pressure from the accreted material driving the infalling gas away and halting the accretion. For a black hole accreting hydrogen-rich gas with a standard opacity, the Eddington luminosity is approximately 1.26 times 10 to the 38 ergs per second per solar mass of black hole. An accreting black hole cannot sustainably exceed this luminosity without the radiation pressure shutting down the accretion. The Eddington accretion rate, the accretion rate corresponding to the Eddington luminosity, determines the maximum rate at which a black hole's mass can grow through accretion. At the Eddington accretion rate, a black hole's mass grows exponentially with an e-folding time, the time required for the mass to increase by a factor of e, of approximately 45 million years, assuming a standard radiative efficiency of 10% for the conversion of accreted mass into energy. Starting from a stellar mass black hole seed of 10 solar masses, the mass of the largest stellar remnant black holes from the first stars, and growing at the Eddington rate continuously, a black hole would reach 1 million solar masses in approximately 560 million years, and 1 billion solar masses in approximately 870 million years. For J1342 plus 0928's black hole of 780 million solar masses to exist at 690 million years after the Big Bang, it would need to have started growing from a 10 solar mass seed at the very beginning of the universe and maintained Eddington rate accretion for every single one of those 690 million years without interruption. Continuous Eddington rate accretion for 690 million years is not physically realistic. Accretion is an episodic process regulated by the supply of gas, the feedback from the accreting black hole's radiation on its surrounding environment, and the mergers and interactions that can both feed and disrupt the accretion flow. Simulations of black hole growth consistently find that even the most favourably placed black holes in gas-rich early environments spend significant fractions of their growth history accreting at sub-Eddington rates, reducing the effective average growth rate below the theoretical maximum. The time available to grow J1342 plus 0928's black hole from a stellar mass seed is simply insufficient, even under the most optimistic assumptions about continuous maximum rate accretion. This conclusion forces consideration of alternative formation mechanisms that begin with more massive seeds, reducing the number of E-folding times required to reach the observed mass. 3 mechanisms have been proposed as sources of more massive seeds. The first involves the runaway merging of stars in the dense cores of early star clusters, where the high stellar density drives frequent stellar mergers that can build up a very massive star of perhaps 1,000 to 10,000 solar masses before it collapses to a black hole. The second mechanism involves the direct collapse of massive primordial gas clouds, clouds of pristine hydrogen and helium that, under specific conditions involving a strong radiation field that prevents molecular hydrogen formation and therefore delays fragmentation into individual stars, can collapse monolithically into a single massive object of perhaps 10,000 to 100,000 solar masses before forming a black hole. This direct collapse black hole scenario produces seeds massive enough to significantly ease the growth time problem. The third mechanism involves the primordial black holes discussed in a previous chapter. Black holes formed in the first second of the universe's existence from density fluctuations in the primordial plasma, potentially with masses already in the range of millions of solar masses, requiring no stellar evolution phase at all. None of these alternative seeding mechanisms is without its own challenges. The runaway stellar merging scenario requires specific conditions of stellar density and feedback that may not be widely achieved in the first galaxies. The direct collapse scenario requires a specific combination of a strong ultraviolet radiation field to dissociate molecular hydrogen and a large enough pristine gas cloud to provide the mass that may be rare in the early universe. The primordial black hole scenario requires density fluctuations significantly larger than those that produce the standard cosmic microwave background temperature fluctuations, implying a modification to the primordial power spectrum. Since J1342 plus 0928's discovery, additional ancient quasar black holes have been found at even higher redshifts. ULS J1120 plus 0641, with a black hole mass of approximately 2 billion solar masses at a redshift of 7.09, corresponding to 770 million years after the Big Bang, was discovered in 2011. By 2025, over 40 quasars at redshifts above 7 have been confirmed, with black hole masses ranging from hundreds of millions to several billion solar masses. The statistical distribution of these objects is itself a constraint on formation models, not just a single extraordinary object, but a population of early massive black holes whose number density at these redshifts exceeds the predictions of models based on stellar mass seeding by factors of 10 or more in some analyses. The problem is not merely that one impossibly massive black hole exists at high redshift. It is that a population of such objects exists, and that population requires a systematic resolution rather than a coincidental explanation for any individual case. The gravitational wave background. In June 2023, 4 independent pulsar timing array collaborations, Nanograv in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array simultaneously announced the detection of a stochastic gravitational wave background permeating all of space. The signal had been accumulating in their datasets for years, and its emergence above the noise threshold in each independent collaboration's data simultaneously, with consistent properties across all four, was one of the most significant announcements in observational astrophysics in decades. What these experiments had detected was not a gravitational wave from a specific identifiable source, not a binary black hole merger or a neutron-star collision, but a diffuse, omnidirectional hum of space-time ripples washing through the universe from every direction simultaneously, generated by the accumulated gravitational wave emission of countless sources throughout cosmic history. Some of those sources are relatively recent and well understood. Others are ancient beyond any other category of astronomical observation. And the most ancient component, if it exists as theory predicts, carries information from epochs so early that no other signal we can detect was present to record them. To understand the gravitational wave background, it is necessary to first understand what gravitational waves are and why a background of them is expected. Gravitational waves are distortions in the fabric of space-time, propagating oscillations in the curvature of space and time, generated whenever massive objects accelerate asymmetrically. Albert Einstein predicted their existence in 1916 as a consequence of general relativity, and they were first directly detected by the LIGO Observatory in September 2015 from the merger of two stellar mass black holes approximately 1.3 billion light-years away. Individual gravitational wave events like the LIGO detections are analogous to individual sound events, a specific crack or rumble from a specific identifiable source. The gravitational wave background is analogous to the ambient noise of a city, the superposition of an enormous number of individually unresolvable sources whose combined effect is a continuous omnidirectional signal with specific statistical properties. The dominant contribution to the gravitational wave background at the nanohertz frequencies to which pulsar timing arrays are sensitive comes from supermassive black hole binaries, pairs of supermassive black holes orbiting each other in the centers of galaxies that have recently merged. When two large galaxies collide and merge, their central supermassive black holes eventually sink toward the center of the merged galaxy through dynamical friction and form a gravitationally bound binary system. As the binary orbit decays through the emission of gravitational waves, the two black holes spiral toward each other over millions to billions of years, radiating gravitational waves at frequencies that increase as the orbit shrinks. The contribution of all such binaries throughout the observable universe to the gravitational wave background produces a spectrum with a characteristic shape, a power law in frequency, that matches the properties of the signal detected by the pulsar timing arrays. This confirmation that supermassive black hole binaries are responsible for the background's dominant component was a major scientific result in its own right. But it is not the component of the gravitational wave background that pushes hardest against the boundary of cosmic prehistory. That distinction belongs to the primordial gravitational wave background, a component generated not by any astrophysical source, but by the quantum mechanical processes of inflation itself. During inflation, the exponential expansion of space-time stretched quantum fluctuations of the gravitational field, vacuum fluctuations that exist at every point in space as a consequence of the Heisenberg uncertainty principle, to macroscopic scales, converting them into classical gravitational waves with wavelengths comparable to the size of the observable universe. These primordial gravitational waves have been propagating through the cosmos ever since, redshifting to lower frequencies as the universe expanded, and their current spectrum spans a range of frequencies from the very lowest accessible, periods comparable to the current age of the universe, up through the nanohertz frequencies probed by pulsar timing arrays, and the millihertz frequencies that will be accessible to the future Laser Interferometer space antenna mission in space. The amplitude of the primordial gravitational wave background is parameterized by the tensor-to-scalar ratio R, the ratio of the power in gravitational wave perturbations to the power in density perturbations from inflation. Current upper limits from the Planck satellite's measurements of CMB polarization constrain R to be below approximately 0.036 at the angular scales corresponding to the largest CMB modes. This constraint means that the primordial gravitational wave background is too weak to have been detected by the current generation of pulsar timing arrays. The detected signal is dominated by supermassive black hole binaries, but next-generation CMB polarization experiments, particularly the Simons Observatory and CMB-S4, will be sensitive to values of R as small as 0.001 to 0.003, and a detection in this range would constitute the first direct observational evidence of inflation through the gravitational waves it generated. Beyond the primordial background from inflation, there are additional potential sources of a gravitational wave background from the very early universe whose frequencies fall in ranges accessible to different detector types. Cosmic phase transitions, moments in the early universe when the symmetry of the quantum fields governing the fundamental forces changed discontinuously, analogous to the phase transition between liquid water and ice, can generate gravitational waves through the collision and percolation of bubbles of the new phase through the medium of the old phase. The electroweak phase transition, which occurred at approximately 10 to the minus 11 seconds after the Big Bang, when the electromagnetic and weak nuclear forces separated from a unified electroweak force, is one such potential source. If the electroweak transition was first order, proceeding through bubble nucleation rather than smoothly, it would have generated a gravitational wave background peaking at millihertz frequencies, directly in the sensitivity range of the Laser Interferometer Space Antenna mission planned for launch in the 2030s. Even earlier phase transitions associated with grand unified theory symmetry breaking, or with the QCD phase transition when quarks combined into protons and neutrons at approximately 10 microseconds after the Big Bang, would have generated gravitational wave backgrounds at correspondingly higher frequencies, in the range accessible to ground-based detectors like LIGO and the Einstein telescope. Cosmic string networks, one-dimensional topological defects in quantum fields that may have formed during phase transitions in the early universe, are also predicted to generate a gravitational wave background with a distinctive spectrum. And the properties of this background carry information about the energy scale of the phase transition at which the strings formed. Most extraordinarily, some theoretical frameworks predict that gravitational waves could carry information from before inflation, from whatever physical state preceded the inflationary epoch. If our universe emerged from a pre-existing contracting phase through a bounce, as in the ekpyrotic or cyclic cosmology models, where a collapsing universe transitioned to an expanding one through a quantum gravitational bounce, gravitational waves generated during the contracting phase could have propagated through the bounce and be present in our universe today. Similarly, if inflation was preceded by a string gas cosmology phase or some other pre-inflationary epoch, the gravitational waves from that phase might have left an imprint in the present-day gravitational wave background at specific frequencies with a distinctive spectral shape, distinguishable from the inflationary signal. The gravitational wave background is therefore not merely the oldest detectable radiation in the universe. It is potentially a window into epochs that predate the universe's own formation, a messenger from the physics that generated the conditions from which the Big Bang emerged. Pulsar timing arrays detect gravitational waves through an extraordinarily precise measurement technique. Millisecond pulsars, rapidly rotating neutron stars that emit beams of radio waves with clock-like regularity, serve as natural gravitational wave detectors because a gravitational wave passing between Earth and a pulsar will stretch and compress the spacetime along the signal's path. advancing or retarding the arrival times of the pulsar's radio pulses by tiny amounts. By monitoring the arrival times of pulses from dozens of millisecond pulsars distributed across the sky over intervals of years to decades, and by looking for the specific spatial correlation pattern in arrival time residuals that a stochastic gravitational wave background produces, called the Hellings-Downs correlation, pulsar timing arrays can detect the background even when no individual wave source is resolvable. The 2023 detection by NanoGrav and its partner collaborations measured the Hellings-Downs correlation with sufficient significance to claim a detection of the background, marking the opening of a new observational window on the most ancient physics the universe contains. The ongoing analysis of the gravitational wave background spectral properties, the detailed shape of how the signal's power varies with frequency, is now providing constraints on the population of supermassive black hole binaries responsible for the dominant component, and beginning to search for deviations from the binary black hole prediction that would indicate additional contributions from primordial sources. The Einstein telescope, a next-generation ground-based gravitational wave detector planned for construction in Europe, and the Laser Interferometer Space Antenna will extend this spectral analysis across a frequency range spanning many orders of magnitude, potentially revealing the contributions of multiple distinct primordial sources and providing the most comprehensive observational survey of the universe's earliest moments ever attempted. Every frequency of the gravitational wave spectrum corresponds to a specific era of cosmic history, a different moment in the first fraction of a second when different physical processes were generating the space-time ripples that have been propagating toward us ever since. Reading that spectrum is reading the most ancient text in the universe. Primordial magnetic fields. The universe is magnetized, not just in the vicinity of stars and planets, where magnetic fields are generated by the motion of conducting fluids and the rotation of magnetized bodies, but on the largest possible scales, in the vast, nearly empty spaces between galaxy clusters, in the cosmic voids that contain almost no matter whatsoever, in the intergalactic medium that fills the observable universe like an extraordinarily diffuse and transparent gas. These intergalactic magnetic fields are extraordinarily weak. Their strength is measured at less than 1 femtogauss, which is less than 1 quadrillionth of Earth's surface magnetic field, itself one of the weakest magnetic fields associated with any planetary body. But their scale is incomprehensible. They permeate cosmic volumes measured in billions of light years, filling spaces where no astrophysical process capable of generating magnetic fields is known to operate. And they have been present in some form since before the first stars ignited, before the first galaxies assembled, since an epoch when no mechanism other than the physics of the early universe itself could have produced them. The detection of intergalactic magnetic fields came from an unexpected observational signature. In 2010, Alexander Neronov and Evgen Vovk, analyzing data from the Fermi Gamma Ray Space Telescope, found that high-energy gamma rays from distant blazars, violently active galactic nuclei pointing their relativistic jets directly toward Earth, were not accompanied by the secondary emission at lower energies that should have been produced by their interaction with the extragalactic background light. When very high-energy gamma rays travel through intergalactic space, they interact with the diffuse infrared and optical photons of the extragalactic background light through electron-positron pair production. The gamma ray converts into an electron-positron pair, which then inverse Compton scatters the CMB photons to lower energies, producing a cascade of secondary emission at Geiger electron volt energies. In a universe with no intergalactic magnetic field, this cascade emission should arrive at Earth within a fraction of a degree of the original blazar direction, appearing as a halo around the blazar in high-energy gamma-ray observations. Neronov and Vovk found that this cascade emission was not detected at the level expected for an unmagnetized intergalactic medium. Their interpretation was that intergalactic magnetic fields were deflecting the electrons and positrons produced in the pair cascades, spreading the secondary emission over a wider angular area than the angular resolution of the Fermi telescope could detect as a halo, effectively making the cascade emission disappear below the detection threshold when integrated over the full solid angle of the cascade. From the absence of the expected cascade emission, they inferred a lower limit on the intergalactic magnetic field strength of approximately 10 to the minus 15 Gauss, a femtogauss, over coherence lengths of at least a megaparsec. Subsequent analyses using different blazar samples, different energy ranges, and different cascade modelling approaches have broadly confirmed this lower limit, establishing the existence of widespread intergalactic magnetic fields as an observational fact. The origin of these fields is the problem that generates such profound cosmological interest. All known astrophysical mechanisms for generating magnetic fields, the convection-driven dynamos of stellar interiors, the turbulent amplification of seed fields in galaxy clusters, the magneto-rotational instability in accretion disks, operate within existing structures and require pre-existing matter with specific properties. They cannot generate magnetic fields in the cosmic voids between galaxy clusters, where the matter density is far too low for any dynamo mechanism to operate efficiently, and where the timescales for field amplification exceed the age of the universe. A magnetic field in a cosmic void must therefore predate the void's emptiness. It must have been established before the matter in the universe segregated into the filamentary cosmic web structure, leaving the voids behind. The fields in cosmic voids are therefore relics of an epoch before the large-scale structure of the universe had formed. An epoch no more recent than a few billion years after the Big Bang, and quite possibly much earlier. Several theoretical frameworks have been proposed for the origin of primordial magnetic fields, and they differ significantly in the epoch at which they predict the fields were generated. The first category involves inflation itself, the same exponential expansion that generated primordial density fluctuations, and gravitational waves could in principle also generate magnetic fields by amplifying quantum vacuum fluctuations of the electromagnetic field. The standard electromagnetic field is conformally invariant, which means its vacuum fluctuations are not amplified by the expansion of space-time in the same way that gravitational fluctuations are. Generating an inflationary magnetic field therefore requires either breaking the conformal invariance of electromagnetism explicitly by coupling the electromagnetic field to a scalar field or to the curvature of space-time, or invoking an extended theory of electromagnetism that naturally lacks conformal invariance. Several such mechanisms have been proposed, and they can, in principle, generate magnetic fields of the required amplitude and coherence length, but they generally require introducing new physics beyond the standard model. The second category involves cosmological phase transitions in the early universe. During the electroweak phase transition at 10 to the minus 11 seconds, and the QCD phase transition at 10 to the minus 5 seconds. The thermal state of the universe changed rapidly and non-uniformly. The boundaries between regions in different phases could have generated electric currents and thereby magnetic fields through the Harrison mechanism, in which vortical flows of charged plasma during the phase transition generate magnetic fields through Faraday induction. The characteristic scale and amplitude of fields generated by this mechanism depend on the nature of the phase transition. First-order transitions generate larger amplitude fields on larger scales than crossovers, and current theoretical predictions for these mechanisms give field amplitudes that are potentially consistent with the observational lower limits on intergalactic magnetic fields. The third and most ancient category involves pre-inflationary physics. If the inflaton field was coupled to the electromagnetic field through a specific type of interaction, or if the pre-inflationary state of the universe involved a form of matter or energy that generated magnetic fields before inflation began, The subsequent inflationary expansion could have amplified these pre-existing fields to macroscopic coherence lengths. Fields generated in this way would have coherence lengths comparable to the size of the observable universe, one of the most distinguishing features of primordial fields compared to astrophysically generated ones. The detection of magnetic fields with extremely large coherence lengths extending beyond the scale of galaxy clusters and into the cosmic voids would be a powerful argument for a pre-inflationary origin. The consequences of primordial magnetic fields extend throughout the history of the universe. In the early universe before recombination, a magnetic field couples to the photon baryon plasma and influences the evolution of the acoustic oscillations that are imprinted on the CMB. A magnetic field with sufficient amplitude would alter the CMB power spectrum and generate specific patterns of CMB polarization, vector and tensor modes, that are distinctive signatures of a primordial magnetic field. Current upper limits from Planck CMB measurements constrain the amplitude of any homogeneous primordial magnetic field to be below approximately a few nanogauss on megaparsec scales, substantially above the femtogauss lower limit from the Fermi-Blazar observations. The allowed range spans 4 to 5 orders of magnitude, and the true amplitude of the primordial field, if it exists, lies somewhere within this range. At later epochs, primordial magnetic fields influence the formation of the first stars and galaxies by providing magnetic pressure that resists gravitational collapse, and by generating additional heating through ohmic dissipation and ambipolar diffusion. The alignment and structure of magnetic fields in present-day galaxies and galaxy clusters may retain memory of the primordial field, particularly on the larger scales where the field has not been significantly altered by astrophysical dynamo amplification. Measurements of the Faraday rotation of polarized radio sources, the rotation of the polarization angle of radio waves passing through a magnetized medium, across large samples of sources at different distances, and directions provide constraints on the coherence properties of the intergalactic magnetic field that help distinguish different production mechanisms. The square kilometre array, with its extraordinary sensitivity and resolution for radio polarimetry across the full sky, will provide a transformative improvement in these Faraday rotation measurements, and may definitively establish both the amplitude and the coherence length of the intergalactic magnetic field, constraining its origin to a specific epoch in cosmic history. The axis of evil. The cosmic microwave background is not simply a record of the universe's state at 380,000 years of age. It is also a statistical object, a single realization of a random process governed by the physics of inflation and the subsequent acoustic evolution of the primordial plasma. The statistical properties of this realization, specifically whether the temperature fluctuations at different angular scales and different positions on the sky are statistically independent of each other, as inflation predicts, carry information about the large-scale geometry and topology of the universe that has no other accessible observable. And when cosmologists perform the most sensitive available tests of these statistical properties, they find something that the standard model of inflation, with its prediction of statistical isotropy and Gaussianity, does not predict. The larger structures visible in the cosmic microwave background are aligned with each other and with the plane of our own solar system, to a degree whose probability of arising by chance is less than 1 in 1,000. The structures in question are the quadrupole and octopole, the temperature fluctuation patterns at angular scales corresponding to roughly 90 and 60 degrees on the sky, which divide the sky into 4 and 8 large, alternating hot and cold regions respectively. In the standard inflationary model, the orientations of these patterns should be completely independent of each other. They are produced by quantum fluctuations during inflation at different wavelengths, and there is no physical mechanism that should cause the pattern at one wavelength to know about the pattern at another. Yet analyses of both the WMAP and Planck CMB datasets find that the dominant axes of the quadrupole and octopole are aligned to within a few degrees. A mutual alignment whose probability of arising by chance from two independently oriented random axes is approximately 1 in 60, rising to approximately 1 in 200 or better when the precise angular separation is accounted for in detail. The deeper and more disturbing aspect of the alignment is its relationship to the ecliptic plane, the plane of Earth's orbit around the Sun. When the combined axis of the quadrupole-octopole alignment is projected onto the sky in ecliptic coordinates, it lies within a few degrees of the ecliptic poles, the directions perpendicular to Earth's orbital plane. The probability of this additional alignment with the ecliptic, given a random orientation for the quadrupole-octopole axis, is approximately 1 to 2%, depending on the specific statistical test. Combined, the probability that both the mutual alignment and the ecliptic alignment arise by independent chance is below 1 in 1,000. Cosmologist João Magejo, recognizing the damage this alignment does to the assumption of statistical isotropy that underlies all of modern cosmology, gave the finding its striking name, the axis of evil. The name captures the theoretical significance accurately. Statistical isotropy, the property that the universe has no preferred direction, is not merely an aesthetic preference in cosmology. It is a mathematical necessity for the Friedmann-Lemaitre-Robertson-Walker metric that underlies the standard cosmological model. The FLRW metric assumes that the universe is the same in every direction from every point, allowing the universe's entire history to be described by a single time-dependent scale factor. If the universe has a preferred direction, if there is a grain to space-time, an axis around which physical processes are not symmetric, then the FLRW metric is not an exact description of reality, and the equations derived from it for the expansion rate, the growth of structure, the CMB power spectrum, and all other cosmological observables are approximations at best and systematic errors at worst. The foreground contamination explanation, the argument that residual emission from the Milky Way is producing a spurious alignment in the CMB temperature maps, is the most technically substantive challenge to the reality of the axis of evil. The Milky Way emits microwave radiation through synchrotron emission from relativistic electrons and thermal emission from interstellar dust, and this emission must be subtracted from the raw CMB maps to isolate the cosmological signal. If the subtraction is imperfect, the geometry of the residual galactic emission could produce a spurious pattern in the large-scale CMB temperature maps. However, this explanation faces a specific quantitative challenge. The Milky Way lies along the galactic plane, while the alignment found in the CMB maps is with the ecliptic plane. These two planes are inclined at approximately 60 degrees to each other. For galactic residuals to produce an ecliptic alignment, they would need to be concentrated preferentially along the ecliptic rather than along the galactic plane, which is not the expected geometry of any known galactic foreground emission mechanism. The Planck satellite's confirmation of the alignment across 9 frequency bands using 4 independent component separation algorithms provides the strongest available argument against a foreground origin. Each algorithm separates the galactic foreground from the cosmological signal using different mathematical approaches and different assumptions about the spectral properties of the foreground components. The fact that all 4 methods produce consistent large-scale temperature maps showing the same alignment is a powerful argument that the alignment is not an artifact of any specific cleaning procedure. If the alignment were produced by residual foreground contamination, it would be expected to vary among the different methods in proportion to the differences in their foreground modelling assumptions. Its consistency across all methods instead suggests that it is a genuine feature of the underlying cosmological signal. Independent support for a directional asymmetry in the CMB comes from several other anomalies that cluster in the same region of the sky. The low multipole power, the anomalously small amplitude of the CMB quadrupole relative to the prediction of the standard model has been measured consistently since the COBE satellite and remains unexplained. A hemispherical power asymmetry in the CMB, in which the amplitude of temperature fluctuations is slightly larger in one hemisphere of the sky than in the other, has been reported at the 3 to 4 sigma level in both WMAP and Planck data, and the axis defining the asymmetric hemispheres is broadly consistent with the quadrupole-octopole alignment axis. The CMB cold spot in Eridanus, discussed in a previous chapter, sits in the same general region of the southern sky. While each of these anomalies individually might be dismissible as a statistical fluctuation, their spatial clustering in a consistent direction raises the cumulative significance of the directional anomaly substantially. The dark flow of galaxy clusters, the coherent bulk motion of thousands of galaxy clusters toward a specific region of the southern sky, measured through the kinetic Sunyaev-Zeldovich effect, points in a direction broadly consistent with the CMB axis of evil. The alignment of quasar spin axes over scales of billions of light years, found in multiple independent analyses of quasar catalogues from the Sloan Digital Sky Survey and other surveys, appears to follow the same large-scale directional structure. These independent datasets, the temperature of the oldest light in the universe, the velocities of modern galaxy clusters, and the orientations of ancient supermassive black holes, share a common directional bias that their different systematic error budgets make very difficult to attribute to a common measurement artifact. The probability that all three signals point in the same direction by coincidence is calculated by several groups to be less than 1 in 10,000, though the precise probability depends on assumptions about the prior probability of the alignment and the independence of the different datasets. If the axis of evil is real, if the universe genuinely has a preferred direction at the largest observable scales, the implications are as fundamental as any discovery in the history of science. The cosmological principle, which has been the foundational assumption of all modern cosmology for a century, would be false as a universal statement. The FLRW metric would be an approximation to a more complex anisotropic spacetime, whose true description requires either a Bianchi cosmological model, an exact solution of Einstein's equations for a homogeneous but anisotropic universe, or some more radical modification. The Hubble tension, the axis of evil, and other large-scale CMB anomalies might be symptoms of the same underlying departure from the cosmological principle, a departure that our standard model systematically ignores. The next generation of CMB polarization experiments will provide the most definitive test through the measurement of E-mode polarization at the largest angular scales. If the quadrupole-octopole alignment appears in the polarization maps at comparable statistical significance, the case for a physical origin will be extremely difficult to dispute. Relic dark matter structures. Dark matter constitutes approximately 27% of the total energy content of the universe, and its gravitational influence shapes every structure from the scale of individual galaxies to the cosmic web that defines the large-scale distribution of matter across billions of light years. Despite this dominant role in the universe's structural evolution, dark matter has never been detected through any interaction other than gravity. Its particle identity is unknown. Its production mechanism in the early universe is uncertain. And the structures it forms, the dark matter halos and subhalos that provide the gravitational scaffolding for galaxies, are among the oldest gravitationally bound objects in the cosmos, their formation beginning within the first seconds to minutes of the Big Bang, when the universe was still a featureless, scalding plasma. The standard cold dark matter paradigm assumes that dark matter consists of particles that were non-relativistic, moving much slower than the speed of light. At the time, they decoupled from the rest of the plasma in the early universe. This thermal history, becoming cold before structure formation began, determines the characteristic mass scale of the smallest dark matter structures that can form. For cold dark matter, the minimum halo mass is determined by the free streaming length, the distance a dark matter particle travels before structure formation begins, which for the most commonly studied dark matter candidates, such as weakly interacting massive particles in the mass range of tens to hundreds of giga-electron volts, corresponds to extremely small masses of approximately 10 to the -6 solar masses, smaller than the mass of Earth. This means that cold dark matter predicts the existence of an enormous number of extremely small dark matter clumps, from the scale of Earth masses up through the scale of the smallest galaxies, forming a hierarchical spectrum of halos and subhalos at every mass scale. These small dark matter halos form first because the density fluctuations in the dark matter distribution are statistically stronger on small scales than on large scales in the cold dark matter power spectrum inherited from inflation. The smallest dark matter halos, those of Earth mass or less, began collapsing gravitationally within the first few seconds to minutes after the Big Bang, when the universe was still dominated by radiation, and the Hubble expansion rate was set by the energy density of photons and relativistic particles rather than matter. These earliest dark matter concentrations, sometimes called microhalos or mini-halos, are among the oldest gravitationally bound structures in the universe, predating the first atoms, the first stars, and the first galaxies by hundreds of millions of years. If cold dark matter is correct, they exist in extraordinary numbers in the present-day Milky Way. Estimates suggest roughly 10 to the 12 such microhalos within our galaxy alone, distributed throughout the galactic halo as a vast and invisible population of sub-Earth mass gravitational structures. The detection of these microhalos is extraordinarily challenging because they are invisible across the entire electromagnetic spectrum. They contain no baryonic matter, no gas, no stars, nothing that emits or absorbs radiation. Their gravitational effects on surrounding matter are the only potential observational signatures. Gravitational microlensing, the temporary brightening of background stars or quasars as a dark matter halo passes in front of them, is the primary technique with sensitivity to halos in the mass range of Jupiter masses and above. For the smallest dark matter, halos below the mass of stars, the microlensing signal is too brief and too weak to be detected with current technology. Pulsar timing arrays, which can detect the tiny gravitational perturbations of dark matter halos passing near the line of sight to a pulsar, have been proposed as a potential probe of dark matter substructure on scales below the microlensing threshold. The presence of relic dark matter structures from the earliest cosmic epochs has implications for the detectability of dark matter through direct detection experiments on Earth. If dark matter is organized into dense microhalos rather than being smoothly distributed throughout the Milky Way's halo, the local dark matter density experienced by a detector on Earth would be highly variable, dominated by the background smooth halo for most of the time, but occasionally enhanced by orders of magnitude when Earth passes through or near a dense dark matter microhalo. This variability would produce a non-uniform detection rate in dark matter direct detection experiments that differs from the smooth modulation expected for a uniform dark matter distribution, and its specific statistical properties would encode information about the mass function and density profiles of dark matter microhalos, and therefore about the conditions of the early universe in which they formed. The properties of relic dark matter structures also constrain theories of dark matter beyond the cold dark matter paradigm. Warm dark matter particles that were relativistic at the time of decoupling and therefore have a longer free streaming length, would suppress the formation of the smallest halos, producing a minimum halo mass scale larger than the cold dark matter prediction. Fuzzy dark matter, ultralight bosonic dark matter with a de Broglie wavelength on the scale of dwarf galaxies, would produce quantum mechanical pressure that prevents the formation of halos below a specific scale and gives existing halos characteristic density profiles with cores rather than the cusps of cold dark matter. Self-interacting dark matter that experiences additional forces beyond gravity, would produce halos with modified core profiles and altered substructure distributions. Each of these alternatives to cold dark matter predicts a different spectrum of relic structures from the early universe, and measuring that spectrum would constrain the identity of dark matter in a way that complements direct detection and collider experiments. The oldest structures in the universe, the dark matter microhalos that formed in the first minutes of cosmic history, carry within their properties the most precise available information about what dark matter actually is. Population 3 stars. The first stars in the universe were not like any stars that exist in the present-day cosmos. They formed from gas of primordial composition, pure hydrogen and helium, with trace amounts of deuterium and lithium, completely free of the carbon, oxygen, silicon, iron, and other heavy elements that characterize the gas clouds from which all subsequent stellar generations formed. They formed in conditions of temperature, density, and gravitational environment that have not existed anywhere in the observable universe for more than 13 billion years. And they lived briefly, explosively, and with consequences that shaped every subsequent structure in the cosmos. The first light after the cosmic dark ages, the first heavy elements in the universe, the first sources of ionizing radiation that began the process of reionization, and possibly the seeds of the supermassive black holes that power quasars and active galactic nuclei throughout cosmic history. These first stars are called Population 3, and they represent one of the most extreme classes of astronomical object that physics permits. The mass of Population 3 stars is the central parameter that determines essentially all of their properties, and it is set by the physics of primordial gas cooling. In present-day star-forming regions, the gas cools efficiently through molecular line emission from carbon monoxide and other molecules produced from heavy elements, allowing gas clouds to fragment into cores of approximately 1 solar mass, the characteristic mass of present-day stars. In the primordial gas clouds of the cosmic dark ages, the only available coolant was molecular hydrogen, which is a far less efficient coolant than CO because its molecular symmetry eliminates the strongest rotational transitions. This reduced cooling efficiency means that primordial gas clouds must become much more massive before their thermal energy is dissipated enough for gravitational collapse to proceed, and the mass scale at which collapse begins is much higher than in the present day. Theoretical calculations of primordial gas cooling and fragmentation consistently find that Population 3 star formation proceeds from protostellar cores with masses in the range of tens to hundreds of solar masses, with some models allowing masses up to 1,000 solar masses or more under specific initial conditions. A star of 100 solar masses has a luminosity approximately 1 million times greater than the Sun, so luminous that radiation pressure becomes a significant force against gravitational accretion, limiting how much additional mass the star can accumulate after reaching this scale. Its surface temperature reaches approximately 100,000 Kelvin, making it a powerful source of ionizing ultraviolet radiation. Its main sequence lifetime is approximately 2 to 3 million years, 1,000 times shorter than the Sun's 10 billion year main sequence lifetime. In those few million years, it fuses hydrogen into helium in its core, then helium into carbon and oxygen, then neon, magnesium, silicon, and finally iron in the onion shell structure of nuclear burning that characterizes the most massive stars. Iron cannot release energy through further fusion. It is the most tightly bound nucleus. And when the iron core reaches the Chandrasekhar mass limit of approximately 1.4 solar masses, it collapses catastrophically in a fraction of a second, triggering a core collapse supernova that expels the star's outer layers at velocities of several percent of the speed of light. The nucleosynthesis products of population 3 supernovae are the first heavy elements ever introduced into the intergalactic medium. The specific pattern of element abundances produced by population 3 supernovae differs from the pattern produced by present-day core collapse supernovae A in ways that reflect the different mass and composition of the progenitor stars. Theoretical predictions for population 3 supernova nucleosynthesis find enhanced production of elements like carbon, oxygen, magnesium, and silicon relative to iron compared to present-day yields, and potentially distinctive patterns in the ratios of odd to even atomic number elements. These nucleosynthesis signatures are directly observable in the most metal-poor stars of the present-day galaxy, the so-called extremely metal-poor stars with iron abundances below 1/10,000th of solar, which formed from gas that had been enriched by only one or a few population 3 supernovae, and therefore preserve in their atmospheres a chemical fingerprint of the first generation of stellar explosions. HD 140283, the Methuselah star discussed in the first chapter, is itself a population 2 star, formed from gas that was enriched by population 3 supernovae before condensing into HD 140283 at the earliest epochs of the galaxy's formation. Its extremely low metallicity places it among the objects most directly connected to population 3 nucleosynthesis. More extreme examples include the star SMSSJ 031300.36-67083.9.3, discovered in 2014 in the Milky Way's halo, which has an iron abundance below the detection limit of conventional spectroscopy, less than 1/10,000,000th of solar, but contains detectable carbon and other elements consistent with enrichment by a single, very massive population 3 supernova. Each of these hypermetal-poor stars is a fossil from the era of the first stars, preserving in its chemical composition a record of nucleosynthesis that occurred within the first 200 million years of cosmic history. The direct detection of population 3 stars themselves, observing them in their original host galaxies at the high redshifts at which they formed, is one of the primary scientific goals of the James Webb Space Telescope's early universe science program. Population 3 stars are expected to produce distinctive spectral signatures in the rest frame ultraviolet, strong nebular emission lines from the surrounding ionized gas, particularly helium emission lines that are diagnostically associated with the very hard ionizing spectrum produced by extremely hot massive stars, and an absence of the metal absorption lines that are present in the spectra of all lower metallicity, but still metal-enriched stellar populations. Webb has begun to find candidate population 3 stellar contributions in the spectra of some high redshift galaxies, with the galaxy GN-Z11 at a redshift of approximately 10.6, showing nitrogen line ratios and helium emission features, potentially consistent with a contribution from very massive hot stars, though the interpretation remains debated. The definitive detection of population 3 stars, observing directly the first generation of light sources in the universe, would be one of the most consequential astronomical discoveries of the era, providing direct observational access to the physical conditions of the universe's first 100 million years. The lithium problem. Among the observational challenges confronting the standard model of cosmology, few are as precisely characterized or as theoretically troubling as the cosmological lithium problem. It sits at the intersection of nuclear physics, stellar physics, and cosmology, connecting the physics of the first 3 minutes of the universe with the chemical composition of the oldest stars in the Milky Way, and producing a discrepancy that neither stellar physics nor nuclear physics has been able to satisfactorily explain in more than 3 decades of sustained effort. The problem is simple to state and difficult to resolve. The oldest stars in the universe contain approximately 3 times less lithium-7 than the standard model of Big Bang nucleosynthesis predicts they should. Big Bang nucleosynthesis is the process by which the primordial abundances of the light elements, hydrogen, helium, deuterium, lithium, were established in the first 3 minutes after the Big Bang, when the universe was approximately 1 second old and had cooled to a temperature of approximately 10 billion Kelvin. The rates of the weak nuclear force reactions that interconverted protons and neutrons fell below the expansion rate of the universe, and the ratio of neutrons to protons was frozen at approximately 1 to 7. Over the next few minutes, as the universe continued to cool through a temperature of approximately 1 billion Kelvin, these neutrons and protons fused into atomic nuclei through a series of nuclear reactions whose rates and outcomes are precisely determined by the nuclear cross-sections measured in laboratory experiments. The final product was a universe containing approximately 75% hydrogen by mass, 25% helium-4, with trace amounts of deuterium at approximately 25 parts per million, helium-3 at approximately 10 parts per million, and lithium-7 at approximately 5 parts per 10 billion. A lithium abundance that is tiny in absolute terms, but precisely predicted by the standard model. The prediction of Big Bang nucleosynthesis for the primordial lithium abundance depends primarily on the baryon to photon ratio, the number of protons and neutrons per photon in the universe, which is also measured with high precision from the cosmic microwave background. Using the CMB derived baryon density, the standard model predicts a primordial lithium-7 abundance of approximately 5 times 10 to the minus 10 relative to hydrogen by number. The measurement of this abundance in the oldest stars of the Milky Way, the most metal-poor halo stars of population 2, which formed from near-primordial gas, and should therefore reflect the primordial lithium abundance in their atmospheric compositions, gives values approximately 3 times lower than the prediction, clustering around 1.6 times 10 to the minus 10. This factor of 3 discrepancy between the predicted and observed primordial lithium abundance, measured consistently across hundreds of halo stars over 3 decades, is the cosmological lithium problem. The most natural resolution would be that the old halo stars have destroyed some of their lithium through nuclear burning, reducing their atmospheric lithium abundance below the primordial value. Lithium is a fragile element. It is destroyed by proton capture at temperatures above approximately 2.5 million Kelvin, which are reached in the convective interiors of stars when material is transported downward from the cooler surface layers where lithium is preserved. In present-day solar-type stars, significant lithium depletion occurs over the stellar lifetime, and the present-day Sun's photospheric lithium abundance is more than 100 times lower than its presumed initial value. For the oldest halo stars, the situation should be different. Their lower metallicity alters the stellar structure in ways that models predict should reduce the efficiency of lithium depletion and the consistency of the observed lithium abundances across a wide range of stellar temperatures and ages. The so-called Spite Plateau, named for the astronomers Francois and Monique Spite, who first identified it in 1982, suggests that whatever process set the uniform observed abundance was acting at the level of the star's initial lithium content rather than through individual depletion histories. The Spite Plateau is itself a profound observation. Across hundreds of metal-poor halo stars spanning a range of effective temperatures from approximately 5,500 to 6,500 Kelvin, and a range of metallicities spanning 2 orders of magnitude below solar, the measured lithium abundance is nearly constant at approximately 1.6 times 10 to the minus 10. This constancy argues powerfully that the observed abundance reflects a universal initial condition, a primordial abundance, rather than the variable depletion histories of individual stars. If stellar depletion were responsible for reducing lithium from the primordial value to the observed value, it would have to operate with extraordinary uniformity across all these stars with different masses, temperatures, ages, and metallicities, producing exactly the same final abundance in each case, despite the different stellar physics. This is not impossible, but it requires a very specific mechanism of lithium transport and depletion that current stellar models cannot reproduce. The alternative resolution is that Big Bang nucleosynthesis is incomplete or incorrect in its prediction for the lithium-7 abundance. Several nuclear physics proposals have been made to reduce the theoretical prediction. The most extensively explored involves an uncertain nuclear reaction rate, specifically the reaction between beryllium-7 and neutrons, which can destroy beryllium-7 before it decays to lithium-7. That might be larger than current laboratory measurements indicate. If this reaction rate was sufficiently enhanced, perhaps due to a resonance in the beryllium-7 plus neutron cross-section at energies relevant to Big Bang nucleosynthesis, the primordial lithium-7 abundance would be reduced toward the observed value. Multiple, dedicated laboratory experiments have been conducted to measure this cross-section more precisely, and none has found the required enhancement within the experimental uncertainties. Other proposed nuclear physics resolutions involve uncertain rates for reactions producing lithium-7 directly or destroying it subsequently, and these too have not produced the required reduction within currently measured uncertainties. More radical proposals involve new physics beyond the standard model. If a new particle with a mass of a few mega-electron volts, lighter than the electron but more massive than the photon, existed in the early universe and decayed into photons or electron-positron pairs during or after Big Bang nucleosynthesis, it would have altered the baryon to photon ratio and potentially reduced the lithium-7 abundance while leaving the helium and deuterium abundances within their observed ranges. The decay of a late decaying particle, one that decays with a lifetime comparable to the Big Bang nucleosynthesis timescale, could also directly disrupt lithium-7 nuclei through photodisintegration or hadronic showers, reducing the surviving abundance to the observed level. These scenarios require new physics that has not been independently confirmed, but that falls within the general class of extensions to the standard model that are theoretically motivated on other grounds. The lithium problem's importance is amplified by what it implies about the reliability of Big Bang nucleosynthesis as a whole. The predictions for the helium-4 and deuterium abundances are in excellent agreement with observations, and this agreement is one of the primary pieces of evidence for the standard Big Bang model. Lithium is the only light element for which the prediction and observation are inconsistent. And this inconsistency is a persistent warning that either the observational measurement is affected by poorly understood astrophysical processes, or the nuclear physics of Big Bang nucleosynthesis is missing something, or new physics operated in the first 3 minutes of the universe in a way that has not yet been incorporated into the standard model. Any of these resolutions, if definitively established, would revise our understanding of the physical conditions that existed before any structure in the universe had formed. The pre-inflationary vacuum. Every entry in this list has described objects and phenomena whose existence approaches the boundary of cosmic prehistory. Objects so old that they formed within the first fractions of a second after the Big Bang, signals that carry information from epochs before atoms existed, structures whose properties trace to physics that operated before the universe had cooled enough to permit chemistry or biology, or anything recognizable as matter in the conventional sense. The inflaton field discussed earlier represents the entity that generated the Big Bang itself, the energy reservoir whose evolution produced the hot plasma that subsequently cooled into everything we observe. But the inflaton field required initial conditions, a specific state from which it began its evolution. And those initial conditions belong to something that preceded the inflaton field's inflationary evolution. That something is the pre-inflationary vacuum, and it is the most ancient and most inaccessible concept in all of physical cosmology. The word vacuum in quantum field theory does not mean empty space in the classical sense. It means the lowest energy state of a quantum field, the state in which no particles are present and the field oscillates only with the quantum mechanical zero-point fluctuations mandated by the Heisenberg uncertainty principle. Every quantum field has a vacuum state, and in the standard model of particle physics, these vacuum states are the ground states from which particle excitations, electrons, quarks, photons, and all other particles are created. The vacuum is not nothing. It is a physical entity with measurable energy density, definite quantum numbers, and specific symmetry properties that determine the physics of the particles that can be excited from it. The energy density of the quantum vacuum, the vacuum energy density, is one of the most mysterious quantities in physics. In the standard model of particle physics, the quantum fields associated with all the particle species that exist contribute to the vacuum energy density through their zero-point fluctuations, and the sum of these contributions gives a vacuum energy density that is many orders of magnitude larger than the observed value of the cosmological constant. The dark energy that drives the current accelerated expansion of the universe. The discrepancy between the calculated vacuum energy density and the observed cosmological constant, extending over 120 orders of magnitude depending on the cutoff scale used in the calculation, is sometimes called the worst prediction in the history of physics, and is one of the deepest unsolved problems in theoretical physics. Its resolution likely requires either a mechanism that cancels most of the vacuum energy density through some symmetry principle, not yet discovered, or a fundamental revision of how quantum field theory and gravity are combined at high energies. In the context of pre-inflationary physics, the relevant vacuum state is not the current ground state of the quantum fields of the standard model, but the state of whatever fields existed before inflation, potentially a unified field state at energies far exceeding anything accessible to particle physics experiments, in which the forces we observe as distinct were unified into a single interaction. The pre-inflationary vacuum was the state from which the inflaton field evolved and from which inflation subsequently emerged. Its properties, its symmetry structure, its energy density, its topology, the quantum fluctuations it contained, determined the initial conditions of inflation and therefore, through inflation's dynamics, determined the statistical properties of the primordial density fluctuations that seeded all subsequent cosmic structure. One of the most profound questions in physics is whether the pre-inflationary vacuum had a beginning, whether there was a first moment before which nothing existed, or whether it existed eternally in some form. The framework of eternal inflation, in which the inflaton field is a fundamental feature of a larger inflating background and individual universes form through quantum fluctuations, implies that the pre-inflationary background has always existed and will always exist, that it is eternal in both past and future directions. In this picture, the concept of a beginning of time as applied to our universe is local rather than universal. Our Big Bang marked the beginning of our bubble universe, but not the beginning of the inflating background from which it emerged. Time, in the inflating background, extends infinitely in all directions. An alternative framework is the Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in 1983. In the no-boundary proposal, the universe emerged from a quantum state in which the concept of time was not fundamentally different from the concept of space, in which space-time near the Big Bang was Euclidean rather than Lorentzian, with no distinguished temporal direction. The universe did not emerge from a pre-existing state in which time was defined and flowing. It emerged from a quantum amplitude, a mathematical object that describes the probability of different geometries that had no boundary in the temporal direction, just as the surface of a sphere has no boundary. In this picture, asking what happened before the Big Bang is like asking what is south of the South Pole. The question does not have a meaningful answer because the temporal dimension, as a distinguished direction with a before and after, only emerges after the universe has grown to a sufficient size. The Vilenkin tunneling proposal offers a different perspective. The universe tunneled quantum mechanically from a state of literally nothing, not a pre-existing vacuum, not an inflating background, but the absolute absence of any space-time, to the inflationary false vacuum state. The tunneling is described by a quantum gravitational wave function, and the process is analogous to quantum mechanical tunneling through a barrier in particle physics, but with the tunneling occurring in the space of possible space-time geometries rather than in ordinary position space. In this picture, there was no pre-inflationary state of any kind. The universe came into being through a quantum fluctuation from non-existence to existence, with no prior condition that could be described in physical terms. These competing frameworks, eternal inflation, no boundary, tunneling from nothing, make different predictions for the properties of the pre-inflationary vacuum and for the observable consequences in the current universe. The no-boundary proposal predicts specific departures from scale invariance in the primordial power spectrum at the larger scales, scales corresponding to the lowest CMB multipoles, that might in principle be tested against CMB observations, though the current data are insufficient to discriminate between models. Eternal inflation predicts that the distribution of cosmological parameters across different bubble universes, the multiverse landscape, is determined by the statistics of quantum fluctuations in the eternal inflating background, which in principle could be tested through the anthropic selection effects it implies for why we observe the specific values of dark energy, dark matter density, and other parameters that characterize our universe. Tunneling from nothing makes specific predictions for the total mass and curvature of the observable universe. None of these frameworks is currently testable in the definitive sense that the term is used in experimental physics. Each makes predictions that are either too uncertain to calculate precisely, too subtle to measure with current instruments, or confined to regions of the universe causally disconnected from us. The pre-inflationary vacuum remains the most inaccessible entity in all of physics, the boundary condition of the universe, the initial state from which everything else follows, the thing that the Big Bang emerged from or was identical with, depending on which theoretical framework is closest to truth. It is the deepest layer of the onion, the entity whose nature, if we could ever understand it, would explain not just why the universe has the properties it has, but why there is a universe at all, rather than nothing. Despite its inaccessibility, theoretical efforts to characterize the pre-inflationary vacuum continue to advance through developments in quantum gravity, string theory, and semi-classical cosmology. In string-theoretic frameworks, the vacuum is not unique, but part of a vast landscape of metastable states, each corresponding to different physical constants and dimensional configurations. Transitions between these vacua, mediated by tunneling processes, provide a possible mechanism for initiating inflation in localized regions of a higher dimensional spacetime. This picture naturally aligns with multiverse scenarios, in which the observable universe represents only a small domain within a far larger ensemble of causally disconnected regions. Another avenue of investigation involves loop quantum gravity, where spacetime itself possesses a discrete structure at the Planck scale. In such models, the classical singularity associated with the Big Bang is replaced by a quantum bounce, connecting a prior contracting phase to the current expanding universe. Here, the pre-inflationary vacuum may be interpreted as the ground state of a quantum geometric phase, whose properties determine the conditions at the onset of inflation. Such approaches suggest that the origin of cosmic structure could be traced to quantum gravitational effects, rather than solely to field-theoretic fluctuations. Observationally, indirect probes of the pre-inflationary vacuum remain the only viable strategy. Features such as anomalies in the large-scale cosmic microwave background, deviations from Gaussianity, or signatures of primordial gravitational waves may encode information about physics preceding inflation. Upcoming experiments designed to measure polarization patterns in the cosmic microwave background with greater precision could potentially constrain competing models. However, the interpretive challenge remains formidable, as many predicted effects are subtle and model-dependent. Ultimately, the question of the pre-inflationary vacuum touches on foundational issues concerning the nature of physical law. Whether the vacuum is determined uniquely by deeper principles or selected from a distribution of possibilities remains unresolved. Progress will likely require a synthesis of quantum theory and gravitation, together with new empirical insights capable of discriminating between competing paradigms. Until such advances are achieved, the pre-inflationary vacuum will remain a conceptual frontier, marking the limit of current scientific understanding while continuing to motivate deeper inquiry into the origin and structure of reality. In this sense, it serves not merely as an initial condition, but as a testing ground for the ultimate unification of physics, where answers about existence itself may eventually be found through deeper theoretical and observational convergence efforts. Before the beginning. Everything in the observable universe descended from something older. The atoms in your body were forged in stellar interiors that ignited from primordial hydrogen clouds that condensed from a plasma that expanded from a quantum state that emerged from conditions we cannot directly observe and can only barely theorize about. The chain of descent from the present moment back to the first fraction of the first second of the universe's existence is the subject of modern cosmology, and for most of that chain, the physics is well understood, and the observational evidence is compelling. It is at the beginning, and before the beginning, that the chain becomes uncertain, and it is precisely at that uncertainty that the most profound questions in science are located. What the objects and phenomena in this list collectively demonstrate is that the boundary between the universe and whatever preceded it is not a clean discontinuity, but a gradient, a region where the physics of the universe we inhabit shades gradually into physics we cannot yet describe, with each step further back in time, introducing new uncertainties and new unknowns. Methuselah's star, the oldest individually resolved object, sits at a measured age that edges uncomfortably close to the age of the universe itself, suggesting that our chronometric tools, either stellar age dating or the determination of the universe's age from the CMB, have systematic uncertainties we have not fully characterized. The cosmic neutrino background and the primordial gravitational wave background extend our observational reach back to 1 second and potentially to the first fraction of a second, where the physics of the fundamental forces is known, but the connection to observable quantities is mediated by processes we cannot directly measure. Baryon acoustic oscillations carry information from 3 minutes into the positions of galaxies that form billions of years later, demonstrating that the cosmic blueprint was drawn before any of its execution had begun. Primordial black holes, if they exist, are gravitational fossils from the first milliseconds, predating every other category of astrophysical object by the full length of subsequent cosmic history. The inflaton field precedes the universe itself. It is the entity whose evolution generated the Big Bang, and the question of its initial conditions is the question of what came before the beginning. The pre-inflationary vacuum is the deepest layer, the condition that preceded the inflaton field's evolution, the starting point from which the chain of descent begins, if it began at all, and was not itself an eternal condition with no starting point. The scientific effort to understand these ancient objects and the epochs they inhabit is not merely an exercise in historical reconstruction. It is the most direct available path toward understanding why the universe has the specific properties it has, why the laws of physics take the forms they do, why the constants of nature have the values they have, why the universe is structured in a way that permitted the evolution of stars, planets, and the beings who study them. These questions may not be answerable within the framework of science as it currently exists. They may require conceptual revolutions comparable to quantum mechanics or general relativity before they can be precisely formulated, let alone answered. But the objects at the edge of cosmic prehistory, the stars whose ages challenge the age of the universe, the particles that were born before atoms formed, the fields that existed before space-time had its current structure, are the observational anchors for those future revolutions. They are what we have managed to learn about the universe's deepest past, and they point consistently and insistently toward the conclusion that there is far more to learn, that the beginning of the universe was itself preceded by something, and that something remains the most important open question in all of science.